Hello everyone. In this particular video, we are going to talk about the different type of selectivity terms we use in organic chemistry. So first of all, let's start with stereoselectivity. So what is stereoselectivity? Basically, it means that the two types of products formed, one of which is major product and the other one is minor, and one has major contribution to product and the other one. Let's just understand this with the example what I'm talking about. So let's start with 2-iodobutane. Okay, it's 2-iodobutane and we are going to eliminate the iodine forming a double bond over here or here. How we are going to do that is by adding a base. So let's suppose we have a base which is in this case potassium tert-butoxide. Okay, so if we add a base to an alkyl halide, what's going to happen is elimination of will occur and we will get various type of alkenes. So what are the alkenes that we can get? We can get trans-2-butene first of all, then we can get cis-2-butene. Okay, this one is cis-2-butene, and we can also get 1-butene. Okay, now we have done the experiment. Okay, if we analyze the percent yield of each of the product, percentage of each product in the reaction in the solution, then we can get this one has 60% contribution to the entire product and to the all the product, and this one has 20% and this one has 20% also. So as we can see, this is the major product and these two are minor, and what we are going to see is the difference between these two, because these two are two stereoisomers. This one is trans and this one is cis, and this is a two entirely different compound. Okay, so let me just erase that. This is none of our concern for now. So as we can see, these two are two different type of chemical species. This one is trans and this one is cis, and this has higher concentration than this. So we can say the following reaction is stereoselective to form trans-2-butene other than cis-2-butene. So what did we understand? That a reaction is stereoselective if both the major and minor products of the reaction are stereoisomer of each other. So as we can see, both products, the major one and the minor one, are the stereoisomer of each other. Then we can say the reaction is stereoselective to form one of the product. Then the types of stereoselectivity. So there are two types of stereoselectivity. These are enantioselectivity selectivity and diastereoselectivity. So what's enantioselectivity? So when both major and minor products are enantiomers, then we can say the reaction to be enantioselective. So for example, we can see here this is a prochiral carbonyl compound, and when we add a nucleophile, we are going to get two types of isomers, R and S, two types of isomer, and these two are enantiomers. And if one of these have major contribution to product than other one, then we can say the reaction is enantioselective to that particular species. Then diastereoselective, As I have started the example with this one. So when the major and minor products are diastereomers, we call it diastereoselective. Next, we are going to learn about chemoselectivity. So what's chemoselectivity? I have written down. A reaction is said to be chemoselective when it has more than one functional group, and the reagent we use specifically reacts with one of them, and others remain unaffected. So let's just take an example. We have two functional groups. Okay, let me just draw it. And just we have something like this. Then here we have a double bond O. Then here we have bond OET. So as we can see, it is a bifunctional group. Here we have two functional groups. Here we have a alkyne, and here we have a ester. Then if we add a reagents, something like say H2PT. Okay, H2 in presence of a metal, which is usually PT or T originally, or we can also take nickel too. So if we add this with one equivalence, okay, so what's gonna happen is it's gonna specifically reduce the alkyne and the ester will remain as it is. So let me just draw it. It will occur something like this. It will be reduced to cis alkene. Okay, so 1 2 3 4 1 2 3 4 then 5 6 5 6. Then we have a double bond here, and double bond O and OET. 1 2 3 4 5 6. 1 2 3 4 5 6. It's always better if you just count the carbons, then you will do less mistakes. Okay, so as we can see, the alkyne is changed to cis alkene and the ester groups remain the same. This type of reaction is called chemoselectivity. Let's just take another example, and here we will take two functional groups. Okay, let's suppose we have a keto group, and an ester group. Here keto, and here we have OET. Okay, so we have a keto group and an ester group in the substrate. Then we are going to add a reagent, which is in this case NaBH4. Okay, NaBH4. Okay, so NaBH4 is known as sodium borohydride. Okay, it is a weak reducing agent which can only reduce the ketone, and it can't reduce the ester, and the ester is remain unaffected and stays as it is. So if we draw the product over there, this will be something like this. Here we have a double bond, and the ketone is now reduced to alcohol, and we have ester as it is. Okay, there are tons of examples. Let me just take another one. let's suppose we have a benzene ring over here, and we have two groups, and here we have an H2, and here we have OH. Here we have amine group, and here we have an alcohol group. So what's gonna happen next? We're gonna add a, so as we can see, it both have both have clone pairs, and we're gonna add a what to say, electrophile. Okay, so in this case, let's add just a simple ester. Here we have an O, and here we have OET. So what's gonna happen in normal condition? If we add some like this, then we will get a product like this. The amine in this case will react to form acetylated amine. Here we have O, and here we have CH3. Sorry, here we have CH3, and this is the CH3 group. This group is now here over here. As we can see, the amine group is now acetylated. But if we take the same reaction and if we just do one different thing, so what's that thing? We have same what to say, reagents over there. Okay, and we just add a base. Only one thing is different. If we are going to add a base now. So what's gonna happen is the reaction will be changed and the product also will be changed. Now the product will be the acetylation will occur at alcohol group, not in amine now. So this will look something like this. We have O, then O, C, double bond, O, and here we have CH3. Okay. So as we can see, these two are different products, and depending upon the condition, we have no base and here we have a base. So we can get two different type of products. This is also an example of chemoselectivity. So why this happen? Because we know that both amine and alcohol group has lone pairs which can be donated to the carbonyl center. Okay, but the donation tendency is more in case of amine instead of alcohol if you compare it to alcohol. Okay, so the amine is, in normal case, amine is acetylated, but if we take base, we're gonna get anions, O negative as well as NH negative, and O negative will be formed fast because it is more acidic. Okay, so we will get a product like this. So this was all about chemoselectivity. So here is the summary. Okay, so chemoselectivity basically means a reaction of the reagent with a particular functional group in the substrate. Okay, here is another example. As I have explained earlier, NaBH4 is a selective reducing agent. So the acetone, or we can say keto group, got reduced to alcohol and nothing happened to the ester group. It remained as it is. Next, we are going to learn about stereospecific. So what does it mean? That is, reaction is stereospecific means only specific type of stereoisomer is formed. Okay, there is no major minor, only one specific stereoisomer is formed in a reaction. Then we can say the reaction is stereospecific. So let me just give you an example. let's suppose we have a what to say substrate like this. We have a hydrogen over here, a chlorine over there. Okay, then we have to mention the stereochemistry. Okay, so let me just draw it, and below the plain bond. Okay, let's suppose here we have a ethyl group, and here we have a ethyl group, and these two are methyl groups. Okay, now what we are going to do is we are performing E2 elimination. Okay, so for E2 elimination we need to have a strong base. So let me just add a strong base, which is in this case NaOET. Okay, sodium ethoxide. So we have this substrate and we are adding sodium ethoxide, which is a strong base. Then what's gonna happen? There is going to be E2 elimination, where this living group will be eliminated by shifting of the CH bond pair to this sigma bond, to making an extra bond pi bond. Then we are going to have a alkene. So what type of alkene we are going to have? Let's just draw it. So as we can see, the ethyl and this methyl have the same plane. Okay, so the ethyl and methyl will have the same side. Then we have an ethyl and here a methyl, so we will get an ethyl over here. So as we can see here, we got a transalkene. Okay, but what if we have done something different? If there is ethyl group over there, okay, if the ethyl group was over there, we could have got a product like this. Okay, so here we would have got cis alkene, but we got transalkene. So what I was saying, that in stereospecific reaction only one specific isomer is formed. As we can see here, the E isomer is formed now, and there is no formation of any other minor products. So let me just summarize again. What is stereospecificity? Okay, so it basically means the formation of only one stereoisomer, or we can say the reaction only occur if a specific stereoisomer is formed. Okay, so here is another example. Here we have a substrate like this, and we have a sodium ethoxide and heat, and here E2 is happening. Okay, so as we can see that this methyl and this methyl are opposite or trans. Then so here we got methyl and methyl is trans, and we got the overall transalkene, and this type of alkene, cis alkene, is not formed at all. If we analyze the product, we can only see this type of product. It is not formed at all.